Hi there, this video accompanies Plane Safety Podcast episode number 72, and in this video here, this segment, I want to have a look at an incident, a really fascinating incident that took place in 1978, some 42 years ago, over the Pacific Ocean, involving a Cessna 188 single-engine Cessna aircraft who unfortunately got hopelessly lost over the open ocean and was aided by an Air New Zealand DC10, came to its rescue, and using some real back to basics, classic stopwatch and compass navigation, they managed to figure out where this guy was and guide him home. And I love this tale. And I was reminded of this the other day when we were doing the Plane Safety Podcast pub quiz, which is available on YouTube as well, so please go and check that out. It was a lot of fun. And I was reminded of this. I kind of forgotten about it. I was reminded that this is a true story. So I went back and read up on it and was refreshed my memory of some of the details here. And I love this because it's, a lot of this stuff that we're going to look at now, it's not really taught anymore at, for commercial pilots or at ATPL theory level. It's kind of brushed over, I suppose. But really in today's modern world of GPS, there's no need for this sort of navigation techniques. Now, back then, of course, in 1978, I don't think they had GPS. They had other methods of long-range navigation, but certainly no GPS, certainly none of the high-tech gadgetry that we have on board today's aircraft. And certainly for this guy in his Cessna single-engine aircraft, he didn't have much in the way of navigational equipment at all. Now, I don't intend this to be a dramatic retelling of the story in any way. I just want to have a look at some of the techniques involved and some of the theory behind it, because I think it's really interesting stuff. And it's not terribly complicated either. You certainly don't need to have a knowledge of navigation or even be a mathematical genius to follow along with this. It's all quite basic, and a lot of it actually is common sense. If you just know some basic facts about the natural world, how the sun and the stars and the earth move around each other, then I think probably most people would figure this out anyway, but certainly you can follow this along. If, however, you do want a dramatic retelling of this story, then there are several places you can go. The first of which, probably the best known of which, is the made-for-TV movie of 1993 called Mercy Mission: The Rescue of Flight 771, starring Scott Bakula of Quantum Leap fame and Star Trek Enterprise, and another gentleman whose name I've forgotten, who plays the Air New Zealand captain. Now, of course, typical Hollywood made-for-TV movie. This was hugely dramatized. A lot of the details were changed. A heavily pregnant wife was plonked into the story to add a bit of suspense, and a big storm at the end adds another dimension. Typical Hollywood as well, that the Air New Zealand captain, some reason, was American. I don't understand that, but basically the basic facts and the plot of the story is all there. Some of it's changed unnecessarily so, but it's a good movie if you've got nothing else to do, and that's available actually on YouTube. You can see the whole thing. Mercy, what's it called? Mercy Mission: Rescue of Flight 771. It's a good movie. Another place you could get a shortened version of this is our very own old curmudgeon. Captain Nick Anderson did a very nice plain tale on this some time ago. I don't remember exactly which episode that was, but I'll put it along the bottom here so you can go and have a look. Very good. And the other place, if you want to read about this incident, is in a fantastic book called Emergency in the Cockpit, or Emergency in the Flight Deck, by a gentleman named Stanley Stewart, and that's available on Amazon. You can even download it as a Kindle book for just a few pounds. And that book's brilliant. It's a collaboration, a collection of stories of daring do and feats of amazing airmanship. And this is one of the stories he tells. So go and check that book out if you like. So as I say, this is not a dramatic retelling of the story, but I will just set the scene for you so we know where we're starting from. So we have this pilot. His name was J. Prochnow, I think is how you say it. And now in the movie, he's portrayed as a kind of a cowboy pilot, I suppose, or inexperienced. But that wasn't the case at all. He was actually a very experienced pilot. He was ex-US Navy. So he knew his stuff, he was experienced, he had lots of hours. And at this time in 1978, he was employed as a ferry pilot. His job was to transport light aircraft of various sorts around the US, around the world. And on this particular occasion, this particular mission, if I turn to my prop over here, my globe, he was transporting this Cessna 188 from somewhere on the west coast of the US. I forget exactly where it was, maybe San Francisco somewhere, I think. Him and a friend of his, there were 2 aircraft they were transporting, and the pair of them were to take it from San Francisco all the way down here to Australia. Now, you don't need to be a geographical whiz to know that in between San Francisco and Australia is an awful lot of ocean. In fact, we like to call that the Pacific Ocean. All 75 million square kilometres of it. Now, there are various stopping off places along the way. Their first port of call would have been the Hawaiian Islands, and then down into the Central Pacific here. There's no big landmass, but there are thousands and thousands of small islands. The Fijian Islands and Samoa and all those others. Thousands of islands. Usually, or most of them are pretty small. Some of them just a few miles wide. So there's vast areas of ocean with no land whatsoever. So navigation, of course, has to be very accurate and well considered. So these chaps, the 2 of them, a pair of them, they'd set off in mid-December from San Francisco through the Hawaiian Islands, and they'd worked their way down, and they'd eventually arrived, you probably can't see it, but here, a place called Pago or Pago, I'm not entirely sure how we're pronouncing that, but down here in the American Samoan Islands. And from there, the next leg of their journey was going to be the nearly 1,500 miles southwest down to a very small island called Norfolk Island. Now, Norfolk Island is down here somewhere. It's probably 400 or 500 miles north of New Zealand. A similar distance south of Fiji. It's a very small island, only 3-ish miles across, and there are no other land masses, no other islands within hundreds of miles. So you can see it's a very small target to hit when you're considering the distances that they were trying to navigate across. Now, as we go along, I'm going to sort of explain various terms. And the first one we're going to start with is nautical miles. Okay, I've said it's roughly 1,500 miles between Pago and Norfolk Island. So, what's a nautical mile? Well, actually, it's a little bit confusing because there's a few different ways we can think about nautical miles. The actual definition of a nautical mile is that it equates to 1 minute of arc on the Earth's surface. Now, what does that mean? So the Earth, here it is a globe. It's round, it's a sphere. Yes, flat earthers, it really is, I promise. Now, it's not quite a perfect sphere. It's actually slightly fatter around the middle, so it's slightly squashed, and that's because the whole thing is spinning, and sort of centrifugal forces means that it's slightly fatter in the middle. It's actually about 0.6% wider around the middle than it is across the poles. But for our purposes, we can call it a sphere. So, being a circle, a sphere, we can divide it up into 360 degrees, right? By convention, when we're talking about longitude, we say that the 0 degrees runs through the Greenwich Meridian, here through London, and then we have 360 degrees all the way around until we get back here. Actually, we stop at 180 degrees on the other side and then start again. And similarly, we have 180 degrees on each side going this way on the north and southern hemisphere. So 360 in all. Each degree can be divided up into 60 minutes, and actually each minute can also be divided up into 60 seconds. But a nautical mile is 1 minute of arc length. So here's Here's a degree. We can divide that up into 60. Now, when we're talking about latitude, that's these lines here. These lines describing how far north or south we are of the equator. All these lines are equally spaced and parallel. So we can say that one unit of distance here, one arc minute, is the same whichever latitude we're at. Okay, so when we're talking about latitude, 1 minute of arc length is always 1 nautical mile. However, if we consider lines of longitude, we see that they're not quite parallel, are they? Because this is a sphere and they all meet at the top. And this isn't apparent when we look at maps. So we need to remember that these lines of longitude are gradually getting closer and closer and closer, and they meet all together at the North and South Pole. So actually 1 minute of arc length longitudinally is not a constant. It's decreasing with increasing latitude. So the closer we get to the poles, the closer these 1 minutes of arc length are. So that's a variable. When we talk about a minute of 1 nautical mile, then that distance can vary. And we'll come back to that a little bit later. It's not too difficult at all to work out a correction for that distortion, if you like. So we have a little post-production note here. I don't think I explained that last bit particularly well. So just to demonstrate that one more time, we can see here, these lines here, these are actually 15 degrees apart. This is 15 degrees apart here, but as we go north towards the pole, you see these lines are still 15 degrees apart, but the true distance between them is getting smaller as these lines converge. So that's what I mean there. So as we get north or south, these lines of longitude get closer together and the true distance between them gets smaller, but this still represents the same number of arc minutes or the same number of degrees across the Earth's surface. So we have another definition of a nautical mile, which is a kind of a standard unit, and that's 1 nautical mile equals 1.852 kilometers, or more usefully for us, we can think of it in feet, and it's 6,076.12 feet. Let's call that 6,000 feet. So 1 nautical mile equals 6,000 feet. Lock that bit of information away and we'll return to that later. So we join our heroes on December 20th of 1978 here in Pago Pago in American Samoa. Their plan was to set off in the very early hours of the 20th in darkness to make the nearly 1,500-mile journey south to Norfolk Island. Now, these Cessnas are not particularly quick. They cruise along at around 100 knots. So we can see that the journey is going to take a good 15 hours to complete. So they decide to set off very early in the morning in the hours of darkness in order to arrive late afternoon in Norfolk Island with plenty of sunlight still remaining, to account for any contingencies, for anything going wrong. Now, December 20th might seem like a good date to be doing something like this. Of course, December 21st, the following day, is the Winter Solstice, which is the shortest day, the day with the least amount of light, if you're in the Northern Hemisphere. But of course we're not. Down in the Southern Hemisphere, they're very odd down there. They do everything either upside down or backwards or possibly both. So the Winter Solstice down in the Southern Hemisphere is actually the longest day. It's the day with the maximum amount of sunlight, the longest period of time that the sun remains above the horizon. That's the following day. So that seems like a good time of year to be doing it, actually, doesn't it? So they've got 15 hours flying in front of them. So they set off from Pago Pago in their heavily loaded Cessnas. These things have extra fuel tanks. They've got tons and tons of fuel, lots of fuel endurance, but they're very heavy. Now, this is one bit that the movie does get correct, and one of the best bits of the movie as well, in my opinion. Now, as any pilot out there will tell you, there is no amount of thrust available or no level of performance calculations that you can make There is no runway long enough to get the aircraft off the ground unless you have in the background dramatic music and you say things to your aircraft like, "Come on, baby, don't let me down. You can do it." Of course, this is all in the movie and they get it absolutely right. This whole takeoff sequence lasts about 5 minutes with music and silly dialogue and the aircraft bouncing off the runway, then coming back down and wobbling, and it's all very silly. But they do get airborne, or at least our hero gets airborne. Unfortunately, his colleague, at that precise moment, he had, I think, a fuel line sheared loose, so the engine of his Cessna lost total loss of power, and he had no option but to, in the darkness, to ditch in the ocean, in the shallow waters off the island there. Now, fortunately, he managed to escape unhurt. He was fine, but it did. The aircraft was a write-off, of course, I suspect, upside down in the ocean. But it did delay them a day, so he was fine, but it held things up. So his colleague, obviously that's the end of the journey for him. He returned home. So our hero, Mr. Prochnow, is on his own. So he sets off eventually the next morning, 24 hours later, 3 a.m. or so in the morning, on the 21st now, on the Winter Solstice itself, alone with a 15-hour journey ahead of him. Now, so what did we say earlier? All he's got is a compass, a stopwatch, that's his main two navigational instruments, and quite a basic radio nav aid called an ADF, an automatic direction finding. Now, when paired with a ground-based radio beacon, which we call an NDB, a non-directional beacon, you can use that to kind of work out, give yourself a rough idea of where you're going. Now, an NDB, it's pretty basic in terms of radio nav aids. It's just a radio beacon. It sends out a signal. It doesn't direct that signal anywhere. It just sends it out in all directions. They often have a second, in fact, they all have a second carrier wave with them as well, which transmits a Morse ident, beep, beep, beep. So when you tune into this NDB, you can listen to the Morse ident and check it's the right one you're listening to. And that was the plan here. There's several fairly high-powered NDBs dotted along various islands along the Pacific from which he intended to take a reading. And that all seemed to be going swimmingly well. He was taking readings, confirming his position, and after some 14 hours or so, he reached the point at which he expected to see the island, his intended point of arrival. But looking out, he didn't see anything. No big deal. Maybe the headwinds were a little bit stronger than he thought, his ground speed a little bit lower. So he carried on. It's not unusual to be 10-15 minutes out on such a long crossing like that. But after 30 minutes, 40 minutes or so, he began to realise that something was wrong, because all he could see was bare ocean, no sign of Norfolk Island or any other island. So he managed to call up Auckland Air Traffic Control on HF radio, high frequency radio. Again, high frequency radio is something we use for long range radio communications because it's got a longer wavelength, therefore can travel a bit further, as opposed to VHF, which is the usual sort of short range frequency range that we use. He was too far out for VHF radio. So communicating on HF, it can be sometimes quite tricky. There's a lot of static. It's quite tricky sometimes to talk over HF. But anyway, he managed to contact Auckland Air Traffic Control and let them know that he was lost. Now, we talked about using the ADF for direction finding on an NDB. You can also do that the other way around. You can use some equipment, some direction finding equipment on the ground to tell which direction the radio signal from the aircraft is coming from. So they tried to do this at Auckland, although it's very tricky with HF radio. It works much better with VHF. So they were able to try a direction finding technique to try and get a distance, a radial to where he was, but they only managed to get a very rough idea, so that didn't really help him much. So he's an hour overdue now, no sight of the island, and he's kind of admitting to himself that something seriously has gone wrong and he's hopelessly lost. Luckily for him, there is an Air New Zealand DC10 not too far away, on its way to Auckland from Fiji, I think it was. Now, even better luck for him was that the captain of that DC10 was a New Zealander by the name of Gordon Vetty. As well as being a super experienced pilot, he was also a qualified navigator, as was the flight engineer, a chap by the name of Gordon Brooks. Now, of course, in 1978 at least, a DC-10 was a pretty modern aeroplane, had some sophisticated navigational equipment, so there was no need to carry navigators on the DC-10. But at the time, Air New Zealand also operated older DC-8s, which did need a navigator. So in order to keep up his navigation license, Gordon Vetty, Captain Vetty, would often go and navigate on the DC-8 just to keep current and keep his practice, keep his skills in practice. Same that for Gordon Brooks. He was still a qualified navigator, and in fact, as a passenger, deadheading was another Air New Zealand navigator. So on board, not only did they have a fantastically experienced crew, they had 3 qualified navigators. So they were contacted by air traffic control, informed that this chap in the Cessna was hopelessly lost, and could they provide any assistance. And unsurprisingly, they were keen to offer any help that they could. So how did the DC-10 crew begin to go about finding where this Cessna might be? At this stage, they're talking to each other via HF radio, but that doesn't tell you anything. HF radio, as we said, can be used for long-range communications, so that doesn't help too much. You could probably narrow it down to one side of the Earth, but that's no good at all in this case. So they needed to somehow narrow the search, try to get a handle on where this guy might be, what sort of direction to head in if they're going to have any hope of finding him. And with thousands and thousands of square miles of open ocean in front of them, that must seem to us mere mortals a pretty daunting task. But this is where it gets really cool. This is, I think, just a brilliant use of the tools at hand and just applying a little bit of basic knowledge. So they had to think about this, Captain Vetty and his crew, and they came up with some really brilliant ideas. So how to start to get an idea of where this Cessna might be. So unfortunately, they didn't have sextants with them, or aeronautical almanacs, which give lots of details about celestial objects and sunrise times and all this kind of thing, sunset times. And certainly our poor fellow in the Cessna had no sextant to hand. All he had was a basic chart and his malfunctioning ADF equipment. But what they did have was a functioning compass, and luckily the sun shining in the sky. Now it's getting quite late in the day at this point, so the sun's getting close to setting, so it's closer to the horizon. And luckily, it's a clear day, no clouds, so the sun is in plain view, which is important here. So the idea was just try and start homing in on him, would be to compare headings to the sun. So what Captain Vetty asked the Cessna to do was to turn westbound and face directly into the sun and tell him his heading, and the DC-10 did the same. And doing so established that the Cessna's heading directly to the sun was 274 degrees, while the DC-10 was 270 degrees, exactly west. So a discrepancy, or a difference between the two headings, of 4 degrees. So what does that mean? How does that help us? Well, if we draw a little diagram here, the sun in this case is essentially a fixed point on the horizon, which is a fixed distance away. If we have our sun over here, there he is, our bright blue sun. If my aeroplane here, my DC-10, if this heading here, pointing directly at the sun, is 270, and the other aircraft's heading is 274, here we go, here's west 270, so 274 is slightly further around here. 274 degrees, which means his bearing, the other aircraft to the Cessna, there we go, that's my Cessna, it therefore must be south of the DC-10. If his heading, the Cessna's heading, had been something less than 270, that would have been put him up here somewhere, which means he would be to the north. But in this case, 4 degrees puts him somewhere to the south. So that's a start. It doesn't tell him how far away he is. Now, let's talk about the sun for a minute. The sun, as we know, this great big ball of fiery death somewhere out here in the centre of our solar system, and the Earth is going around the sun, and the Earth is spinning at the same time. And as we know, the Earth spins once every 24 hours. Therefore, the sun comes up, goes down once every 24 hours. Or put another way, we'll see the sun rise on one side of the planet, on the eastern side, move across our sky, moving apparent to us, and then set in the west. And knowing that it takes 24 hours to go around, we can then work out pretty simply that it will travel 15 degrees across the sky every 1 hour, because 360 divided by 24 is 15 degrees per hour. And we can subdivide that again to work out that the sun will move 1 degree across our sky every 4 minutes. So that's useful information to know. And you can do all kinds of clever stuff with this as well. You know, for a little thing you can do with the kids, for instance, you could try and work out what time it is without looking at a watch. So, and for goodness sake, don't look directly at the sun. Health and safety warning here. Don't look directly at the sun. But if you've got, most iPhones and smartphones these days have a compass app on them. What you can do, go out and take a reading towards the sun. Don't look directly at the sun, but you can look at a heading and work out which way you're facing the sun. And knowing that it takes 24 hours to go around, we know that noon, midday, local noon, will be when the sun is exactly south of us. South is a heading of 180. So if we go out and we can see that the sun actually, at whatever time of day it is, let's say it's heading 210, that's 30 degrees off from south. And we know that the sun travels across our sky at a rate of 15 degrees per hour. Therefore, 30 degrees equals 2 hours later. So 2 hours afternoon would be 2 p.m. local. And you can work that out just by looking at the sun. It's quite good fun, something to do with the kids. And we can use some of that information here to try and further home in on this Cessna's position. So, like we said, they didn't have a sextant to hand, which would have been super useful around about now. But what we do have is our fist. And it's a good bit of info, good bit of trivia, but the average fist, the average human adult fist, if you hold it out at arm's length like this and hold it up to the sky, that fist length equates to around about 10 degrees of angular distance on the sky, about 10 degrees. Now, of course, everyone's fist is slightly different. Some have got smaller or bigger fists, but it's a good sort of bench post to work from. A fist held out is roughly 10 degrees, or each finger is roughly sort of 2 degrees. Now, this is very rough and ready sort of a method of working out angular distance in the sky, but it's all they had. So Captain Vetty asked the Cessna pilot to do just this, to try and measure the angle between his horizon and the sun, the setting sun. And they did the same thing on the DC-10 and compared results. So the Cessna pilot, he wasn't able to hold his hand completely out because that would be through the windscreen, but he was able to hold his fist out, and he measured that the distance between the horizon, his local horizon, and the bottom of the sun was roughly about 4 fingers worth, or about 8 degrees if we're saying that each finger is about 2 degrees. So his sun, for him, was about 8 degrees high in the sky at that time. For the guys in the DC10, they measured it to be about half of that. They reckoned it was about 4 degrees above the horizon. So that tells us something straight away. If the sun is higher for the Cessna, then it's earlier in the day for his local time because the sun is higher, right? Which means earlier in the day means he's further west. Obviously, as we go west around the world, the time zones mean the local time is earlier and earlier and earlier. So, for instance, the time here in the UK is about 2 o'clock in the afternoon, which means on the west coast of the States, it's about 9 a.m. because they're further west. And we can use that same principle here. If the sun is higher in the sky, if we're getting towards sunset, then it must be earlier in the day, which means they must be further west. So that's great. He's worked out just by looking at the sun. They've worked out that the Cessna is somewhere south of them and somewhere west of them. So it's southwest. So now we're starting to make progress, right? And now we can even take that one step further. We can start to get an idea of how far to the southwest he is just by using those few basic facts. Now, again, these are very rough and ready measurements. These rules of thumb that we're going to talk about are not at all precise, but they start to give us an idea. They're a rough guide. So, as we said, the Cessna measured the sun angle to be about 8 degrees above the horizon. The DC-10 said it was about 4 degrees. That's a 4-degree difference. So what can we do with that? Well, as it turns out, we can actually directly translate that angular difference into a distance. Remember the way he said that 1 degree equals 60 minutes of arc, and we've said that each minute of arc equates to 1 nautical mile. So, if there's a 4-degree difference in sun angle, 4 times 60 equals 240, right? 240 nautical miles away. Except that's not quite true, because as you remember earlier on, we said that as you move away from the equator, as you get further north and south, those arc minutes start to get closer and closer and closer together until they all meet at the pole. So we need to make a small correction to that 240 nautical miles that we've measured from the sun. And actually it's super simple to do. To find the equivalent measurement at latitude, you just take the cosine of that latitude, and we're at roughly 30 degrees south down here. Here's the equator, which is obviously 0 degrees. We've got the two tropics at 23.5 degrees. Those are the points that mark the sun's highest point in the sky throughout the year, the two tropics. And we were slightly further south of that down here at around about 30 degrees. Now, of course, we've all got calculators on our iPhones, so we can instantly work out what a cosine of any number is. These guys, they probably had this knowledge in their heads, being qualified navigators. It's the kind of stuff that they might use regularly. But actually, the cosine of 30 is roughly 0.87. So all we do is multiply that 240 miles by 0.87, and that comes out as a distance of roughly 210 miles. So now, just using the sun and a compass and a little bit of knowledge, we worked out that the Cessna is south of us, he's to the west of us, and he's about 210 miles away. Brilliant. We're really making progress now. So everything that the DC Crew 10 have done up until now, whilst pretty inspired, I would say, these are very approximate calculations. I'm sure it would be fair to say that they expected there to be potentially some very large errors in what they came up with. I think generally their southwesterly direction is solid, and their rough distance of 210 miles is something to work on. But you know, there's a lot of room for error here. Like we said, people's fists are different sizes. It's very hard to take an exact measurement of the sun in a cockpit with a fist. If it's held this far or this far, it makes a big difference. Maybe the cockpit's being buffeted around by some turbulence. It's not an exact science at all. But they've got another trick up their sleeve here. Now, as we said, so far they've been communicating on HF radio, which is a long-range frequency that we use. But at 210 miles, if that's vaguely accurate, that starts to put them within VHF range. And they can use that if they can work out the point at which they're within VHF range. That will give them an idea of a more thorough idea, a more exact idea of how far away the Cessna is. But how do we know, or how do they know exactly how far that cone of VHF reception is? Well, again, they can work it out, and we can work it out, and it's not particularly difficult. There's an equation that will be well known. We see it at ATPL commercial theory studies. And there's an equation to work out VHF range. Again, this isn't an exact answer, it's approximate. Whilst VHF radio doesn't suffer from the same drawbacks as HF radio, it's not bounced off the atmosphere in quite the same way. It can still be, it still has errors, it can still be reflected a little bit by local terrain, and it depends very much upon the power output of the transmitter. So again, these equations that we're about to look at, it's not an exact answer that we're going to get, but we can work out pretty approximately VHF radio range with the following equation, and that is 1.25 times the square root of the height of the transmitter. That's the basic equation. Now sometimes you see this is written as 1.26 or 1.24. Like I said, it's approximate, but if we plug these numbers in, we find that 1.25 times the square root of the height of the transmitter. The transmitter in this case is the Cessna, it's the radio antenna on the Cessna, and he was cruising along at 8,000 feet. So this number here is 8,000. And what we find, 1.25 times the square root of 8,000, is 111. So that's 111 nautical miles of radio range from the Cessna. Now, but it's not quite as simple as that. If we imagine the Earth's surface and the Cessna's up here, so he's got this radio cone of 111 miles. So beyond that, you're over the horizon, you won't receive it. This is line of sight we're talking about here. But of course, the Cessna's not talking to someone on the ground. The Cessna is talking to this DC10, who's up here at 33,000 feet. So actually the radio range is going to be a bit more. So we have to consider the height or the altitude of the DC10 as well. So what we do, we can take the difference between these two altitudes, 33,000 and 8,000, which is of course 25,000, and we can do that exact same sum, 1.25 times the square root of 25,000, and we find that that's actually 197 nautical miles, which I think we can just round that up, we'll call that 200 nautical miles. So that's the VHF radio range, 200 nautical miles. That's how far apart these two aircraft will be when they first come into contact with each other. So 200 miles that way. Of course, the total line of sight is going to be double that. It's going to be 200 that way, 200 that way. So total radio range, total line of sight of about 400 miles. But the bit we're interested in is the range between the two aircraft, the VHF range between the two. That, taking the difference of the two altitudes and doing this rough and ready sum, gives us round about 200 miles. So now this is good news. They had worked out earlier on that they think that their range between them at that moment is about 210 miles, and they should be within VHF communications within about 200 miles. So they're close. They're really close, in fact, to being within range, VHF range. So what they have him do, and what he'd been doing the whole time in fact, is as well as talking to them on HF radio, the Cessna pilot had also been transmitting on VHF radio on the guard frequency, or the emergency frequency, 121.5. Guard. I'm sure there was someone out there, I'm sure there was someone out there who said that, guard. But with the DC-10 racing southwest towards where they thought the Cessna would be, they should be within just a matter of minutes, be within VHF range. And in fact, that's exactly what happened. Just a few minutes later, they started to hear loud and clear on 1215 the transmissions from the Cessna somewhere in front of them. So this is great. This confirms their initial estimates and that they're getting closer to the Cessna. So what happens at this point is they have the Cessna turn around, instead of flying west away from them, have him turn directly eastbound, and they're flying westbound, so hopefully their closing distance now is that little bit faster. The Cessna's going at about 100 knots, the DC-10's going at about 500 knots. They're closing with 600 knots per hour, so they should be over the same position within 20 minutes or so. So hopefully, problem solved. All they've got to do is somehow make visual contact when they meet, and that's their next conundrum. How are they going to get sight of each other? The Cessna's a pretty small aeroplane, all the way down at 8,000 feet at sunset, which doesn't make viewing easier, and the DC-10's all the way up at 33,000 feet. So what can they do to aid visual contact? Well, it goes without saying that all the lights will be turned on, but it's still broad daylight. I don't think that's going to help much. What they need is some way to make themselves more visible. And the answer they come up with is vapor trails, contrails. We see them all the time in the sky. Aircraft producing long, cloudy tails. But were they producing a contrail? It's not always the case that aircraft cruising at altitude are producing this contrail. And it's very hard to predict actually when you will. So the easiest thing to do is actually to go and have a look, which is exactly what they did. They turned the aircraft through 40 or 50 degrees or so and looked out of the window. And unfortunately, for those atmospheric conditions, they were not producing a contrail. Now, a quick note here. What is a contrail? Well, it isn't a chemtrail. That much we can be certain. Okay, it's not some government conspiracy to control the population. It's formed pretty much in the same way that a cloud is formed. It's water vapor being condensed out of the atmosphere. And you need a very particular set of atmospheric conditions to enable a contrail to form. And that's, as we've seen, that's not always present. But basically what we have, the air coming out of the back of the engine, the thrust, is very hot air. It's also quite humid air. Contains some other stuff, a little bit of chemicals, sulfur, and byproducts of combustion. So it's hot, wet air with some other bits thrown in. So as that air is chucked out the back of the engine, in the immediate local area, the water vapor content in that parcel of air is suddenly and quite rapidly increased as you get this moist air pumped out the back of the engine. So that increases the local humidity of the air, and then if that humidity reaches the saturation point of the air, so if the air can't hold any more water, then that water vapor condenses out of the air. Now, it's obviously up at altitude 33,000 feet. It gets pretty cold. The temperatures are usually down into the minus 30s, minus 40s, so that will freeze pretty rapidly. And now that process is helped by some of the other byproducts that are in that exhausted air, so that the sulfur molecules, other bits and bobs. It's something for the water vapor to latch onto, and it instantly freezes and crystallizes, and that produces a contrail, produces a nice long cloud. And again, depending on the atmospheric conditions, that vapor trail, that frozen contrail, might stay there visible for a very long time, or it might disperse very quickly. It's actually pretty difficult to know if you're going to produce a contrail. There's a lot of variables involved. Various Met Office, particularly back in the war, the Met Office here in the UK used to produce a chart called I think it was called a Mintra chart, which was the minimum minimum trailing level or something like that. But this is used by the bomber fleets, for instance. If they knew at what altitude they would start to produce contrails, vapor trails, and they would stay below that altitude so that they didn't get seen. Of course, in this case, the objective is entirely opposite. The DC10 wants to be seen, but unfortunately, they're not producing any contrails. I think they played around with altitude a little bit. They went up a bit, they went down a bit. But unfortunately, the atmosphere wasn't playing ball this particular occasion, so no contrails. Well, what else could we do? How else could we produce a contrail-like thing? Well, there's the one secret way, which is that secret button on the cockpit that we don't ever talk about. Chemtrails, where we produce those mind-altering chemicals into the atmosphere to control the population. No, just kidding. They didn't use chemtrails. But they did have something else at their disposal. It just so happens that one of the crew members on the DC-10 just quite recently on a previous trip, they'd had to, for whatever reason, dump fuel. And he remembered seeing that this fuel dumping produced a very long trail in its wake, similar to a contrail. So they thought, well, why don't we dump fuel? Most big aircraft, and certainly the DC-10, had ports on the end of its wings, valves that could be opened up, and the fuel would come streaming out at quite a rate, something like 1 ton every minute, something crazy like that. Now, it so happens that this DC-10 was coming from Fiji to Auckland, and at the time, fuel prices in New Zealand were very, very high. So it made sense to tanker as much fuel as possible. We talked about tankering on a few episodes ago on Plane Safety Podcast. Go and have a listen to that. But it made sense for them to fill up their DC-10, fill up the fuel tanks in Fiji and transport that fuel. Now, it costs a little something in extra weight, but overall it makes economic sense to carry all that extra fuel. So for a DC-10, this is actually quite a short leg, Fiji to Auckland. I think it was only maybe 2 or 3 hour flight. And so they had loads and loads of extra fuel on board. They had plenty of fuel to be able to spare a little for fuel dumping in order to produce this trail which would be visible to the Cessna pilot. So that's exactly what they did. After the elapsed what they measured to what they thought would be roughly 20 minutes before they were in the same area, they opened up the dump valves and started producing these lovely long lines of fuel vapor behind them, which hopefully the Cessna pilot could just look up in the air and see. But unfortunately he did not. That was not the case. He looked and looked and looked but didn't see anything. And in fact they tried this twice. They produced some, trails 30 or 40 miles long, but our fellow in the Cessna just wasn't seeing them. So this must have got their heads scratching at this point, wondering why this wasn't working. They'd worked out, remember, using the sun, that the guy was to the south of them, to the southwest of them. He was roughly 200 miles away, which they confirmed with radio VHF radio ranging. They'd worked out that they must be within 200 miles, but yet he couldn't see the contrails. So something clearly wasn't quite right. So everything they've done up until this point has led them to believe that the Cessna is located somewhere down to the southeast of Norfolk Island. So whilst they tried to figure out what to do next, a sensible thing to do would be to have the Cessna fly in a northwesterly direction to hopefully start closing the gap between him and dry land and safety. So have him flying hopefully towards Norfolk Island. So that's exactly what they did. They had him turn northwest and start heading up that way. So hopefully that was going to help in some way later on. But in the meantime, they needed some other way to figure out where this guy was. They'd use the sun to work out he was to the southwest. They'd use the sun angle to calculate he was about 210 miles away, and then they confirmed that later on with VHF radio reception They'd worked out the range should be 200 miles or so when they came in contact with him. So everything so far seems to be tallying up. So quite why they haven't managed to make contact with each other visually is a bit of a mystery, but they haven't. So they need to come up with something else. And what they do, they start a search technique called an Aural Box Search, Aural Box technique. And this is really cool. I really love this. And it's not terribly complicated either. You can follow me through with this one. But it's quite basically what it involves is plotting on the chart the points at which they make and lose VHF radio contact, plotting those points on a chart and then working that backwards to try and work out where the Cessna would be. So the DC10 had been trucking along southwest bound. This is a representation of a chart. These are lines of latitude here. Let's call this one over here 30 degrees south. It's roughly where Norfolk Island is. These lines here, longitude, it's something like 178, 179 degrees east. So the DC10 had been heading southwest towards where it thought the Cessna was. And it made VHF radio contact over here. Okay, let's call that point A. So they've plotted the time and position at which they made radio contact. Now, what is this point? Well, basically this point is a point on a circle with a 200 nautical mile diameter, because that's the VHF radio range. So this point here is somewhere on a 200 diameter, radius circle, a 400 nautical mile diameter. Now, it could be a circle over here. It could be a circle over here. It could be a circle over here. We don't really know at this point where exactly on the circle this point is. Nonetheless, we plot that down. So they carried on, here we go, going southwest towards where they thought the Cessna was. So they got to the point where they thought it was. This is where they did the fuel dumping, tried to produce a nice big visible trail, but that didn't work. So they have the Cessna, wherever he is, hopefully here somewhere, heads off northwest towards Norfolk Island. So this aural boxing technique has them carry on a southwest track going off down here. And they keep on going and they keep talking to him. And at the point at which they lose radio contact, let's say it's down here, they plot that position. Let's call that point B. So this is the point at which they lose radio contact. And again, that's another point on this circle. We still don't know if this is the circle here or if this is the top of the circle. We don't know that yet. So what we do, once we're outside VHF radio range, we make a turn, in this case to the left, 90 degrees to the left. We make another turn to the left, and then a second turn to create a track running at 90 degrees to the first. Now we fly off in this northwesterly direction. So this angle here is 90 degrees. And as we fly off this track here, again, we note the time and the position at which we regain VHF radio contact. So we regain VHF radio contact here at point C, and we carry on, and then we lose contact again up here at point D. Now these 4 points, although my scale admittedly is completely off here, so you'll forgive me for that, but these 4 points now are points on this circle. Not a very good circle, but that's what they are. So how does that help us? Well, you may remember back to your high school geometry classes that if we take these two lines here, these track lines, these are called sectors. Okay, if we bisect this line at 90 degrees, and bisect is just a fancy way of saying cut in half. So if we find the exact halfway point between point A and point B, and then draw a line through it at 90 degrees, that's 90 degrees. And then we do the same for this other line, point C and D. If we bisect that line, let's say the halfway point was down here, that's 90 degrees. You'll remember from your high school geometry, if you bisect lines on a circle, the point at which they intersect is always the very center of the circle. So that's pretty cool. Bisecting lines intercept at the center of a circle. So therefore, just by using these two tracks, this southwest track and this northeast track, we can then work that back with a bit of basic knowledge to work out that the center of that circle, the center of the radio transmissions, and hence the position of the Cessna, must be right there. X marks the spot. Now, I really love that. I think that's a fantastic application of just basic mathematics to solve a real world problem. Now, they had to make a few corrections to that because, of course, the whole time that they were doing this, the Cessna was flying northeast, so they had to work out how much ground he had covered in that time and adjust that. Remember, these legs between points A and B and C and D, these are hundreds of miles long, so that took them quite a bit of time to do this. This wasn't a quick process, it took quite some time. It occurs to me, I'm not sure why they didn't do this, but perhaps if they had either reduced their altitude or had the Cessna climb up, what they would want to do is reduce the distance, the VHF radio range between them. That would therefore reduce the length of the legs necessary to complete this aural boxing process. So perhaps they could have done it a little more quickly by descending. Does that make sense? I'd have to think that one through, but that seems to make sense. So that was aural boxing. Pretty cool, huh? Now, by this time in the whole saga, it's getting pretty late in the day. The Cessna has been airborne for something like 17 hours at this point, so he's getting tired. He's certainly beginning to get concerned about his fuel state. But also the light is fading. The sun is beginning to set in the west. But actually, this could be of use. So Captain Vettel has got one more trick up his sleeve, and it's particularly cunning. I like this a lot. We can use, or he could use, he realised, if they measured the exact time at which the sun set, they could compare the times, and in a similar method that we looked at earlier, where we held the outstretched fist to measure sun angle, which equates to a distance on the ground, we could use the time of the sunset to work out a distance, because we know the rate at which the sun is moving, or apparently moving, across our sky. We know that it goes at 1 degree every 4 minutes. So we can use that. Or he realised that they could use that. So here's what they did. They asked the Cessna pilot to measure to time, make a note of the time, the exact time as accurately as possible at which the upper most extremity of the sun dipped below the horizon. So they wanted him to note that point. I think we've probably all seen that before, haven't we? When the sun is very, very low in the sky, you can start to look at it and you can see that exact point at which the very last slither of light disappears below the horizon. Now, that's not an exact time actually, because it turns out that light does some funny things. It kind of diffracts or refracts, whichever one it is. It does some funky stuff. It kind of, the light is bent around a little bit by the atmosphere. So we can actually see it slightly after it's truly already set. But good enough for government work, as they say. So they had Mr. Cessna record that exact moment that the upper limb of the sun dipped below the horizon. And what they also did, the DC-10 crew had the guys at the air traffic control tower on Norfolk Island do exactly the same thing. So what you need is a ground measurement. You need to know exactly what time the sun sets on the ground, so you can compare those two times. So the chaps out in Norfolk Tower, and this is kind of depicted in the movie, by the way, but they changed some of the details quite a lot. I don't know why, but they do. So the guys in the tower on Norfolk Island note the exact time, as does the Cessna. And then by comparing those two times, we can convert that to a distance. But there's something that we have to take into consideration. If we just took those two times as they are, we're actually going to get quite a large error. And why is that? Well, think about it. The Cessna is not at ground level, so he's not comparing like with like. He's up at 8,000 feet altitude. So they would need to take that difference into account. So he's seeing the sun set from a different angle. He's higher up actually, so he's seeing the sunset a little bit later than he would on the ground. So you need to correct for that. And actually, we can figure that out with a little bit of thought. It's not terribly difficult, and we can figure that out using something every aviator is taught at PPL Navigation Lesson 1. It's a very powerful tool called the 1 in 60 rule. And we use this in all sorts of situations. This is the bread and butter of basic aeronautical navigation. The 1 in 60 rule, it says this. Let me draw it out for you. So, it basically says that the 1 in 60 rule, over a distance of 60 miles, point A, point B, this length here is 60 nautical miles. A 1 nautical mile cross-track error results in an angle down here of 1 degree. So being offset here at 60 miles by 1 mile equals an error of 1 degree. If you were 2 miles off course here, this would be 2 degrees, or if you were at 120 miles, that would be, and you were 1 mile off, that would be half a degree, and so on. So you can imagine how you might use this. You're flying along, here's your route, you're going from this point over here to this point here. You're flying along VFR. At some point over here, let's say this was 60 miles as well, let's make the maths nice and easy. This is 60 miles and this is 60 miles. You look down and you see there's a big lake here, and you look at your chart and you realize that this lake is 1 nautical mile north of your intended route. So you can use this 1 in 60 rule to work out that you will need to turn 1 degree to the left to parallel this track, and a further 1 degree, so 2 degrees, to arrive at your point here. So that's the 1 in 60 rule. And this is particularly useful, and we can use it in this very case here with the sunset. So what we're trying to do here is to establish the time correction we need to apply to work out the same time of sunset on the ground, on the position below the Cessna, because remember, he's at 8,000 feet, so he's seeing the sun set slightly later than he would at the same position if he was on the ground. So we need to work out how much time that relates to, so we can get accurate time figures to work out a distance later on. And as I say, we can use our 1 in 60 rule to work this out. Now we need to round out some of the numbers here. So he's 8,000 feet altitude. For ease of mathematics here, let's just say he was at 6,000 feet altitude. It's close enough. We can fudge it a bit later on. So he's at 6,000 feet altitude. Now, you remember earlier on when we were talking about nautical miles, we said that 1 nautical mile as a standard unit is just over 6,000 feet. So that's handy. So he's, give or take, he's 1 nautical mile high. And we also know the distance to the horizon. We talked about that earlier when we were talking about VHF radio range. Well, what we were talking about there is really line of sight. Okay, and we can use exactly the same calculation, at 1.25 times the square root of the altitude, to work out distance to the visible horizon. And if we're assuming he's at 6,000 feet, again we're fudging a little bit. So if we do that same sum, we can work out that the visible horizon is at about 120 miles. We're rounding the figures a little bit here to make it easy. But that again is handy. So we've got, he's 1 nautical mile up and he's 120 nautical miles from the horizon. And we can assume that the sun, although the sun is in reality many hundreds of millions of miles away, it's a point on the visible horizon. Okay, so we've now got 2 measurements, 1 mile here, 120 miles here. So we can use our 1 in 60 rule. We know that 1 mile at 60 miles equates to 1 degree over here, but we're double that. We're 120 miles away, 1 mile up. So this angle over here is half a degree. So we're looking we've got an error there between us and the ground of 1/2 of a degree, 0.5 of a degree. So what can we do with that? Remember, we're trying to work out a time correction to apply to our sunset time. So we're viewing the sunset 1/2 a degree higher. We know from our earlier discussions that the sun moves across the sky or it moves across our apparent sky at the rate of 1 degree every 4 minutes. So for it to cover 1/2 a degree, it therefore must take 2 minutes. So therefore we can say that since we know the Cessna pilot is viewing the sunset slightly later than he would on the ground, and we've worked out that that correction factor is in fact 2 minutes, we can say whatever time he took for sunset up here at 6,000 feet, 8,000 feet, it would have been 2 minutes earlier on the ground. So now we can use that to compare directly between that time and the time that they measured sunset at Norfolk Air Traffic Control Station. And that's exactly what they did. And they came up with a measurement, a difference of sunset time of 22.5 minutes. And we can use that now. We can use that to directly come up with a distance or a number of degrees. So 22.5 minutes. 22.5 minutes at 4 minutes per degree equals 5.5 degrees. So he's 5.5 degrees away from Norfolk Station, and 5.5 degrees, we said there's 60 miles or 1 nautical mile per minute, and there's 60 minutes in a degree. So therefore 5.5 degrees times the 60 nautical miles corrected for the latitude, so we take the cosine of the latitude, gives us an answer of 242-ish miles. I hope we all followed that. So they worked out he's 5.5 degrees east of Norfolk Island, and 5.5 degrees at 30 degrees south latitude equates to about 240 miles. So I love this, just by using some simple measurements of time and the sun and a little bit of knowledge, we've now worked out a fairly good ranging for him from Norfolk Island, 242 miles. And actually, this all jives completely with what they've been seeing so far. So how they haven't come into visual contact is a bit of a mystery. But this is great news. It also means he's within a couple of hours flying time of safety in Norfolk Island. So it's looking potentially a little bit rosy. So this is brilliant. Off he sets. His fuel state, of course, is still very much an unknown. Will he have enough fuel remaining to fly 2 more hours? We're going to find out. We are approaching the end of this story. Just to put it into context, there's a lot of things been happening here, and actually a lot of this stuff was going on at the same time. So whilst they were making this measurement of the sunset time and coming up with this calculation, they were doing this aural boxing technique, which must have taken a good hour, maybe more, to complete, because they had such long tracks to fly across, you'll recall. So there was a lot of stuff going on, but it was all kind of all jiving together, and everything was suggesting that this guy was indeed some 200 odd miles to the southeast of Norfolk Island. So off they went again, hopefully to overfly his position, and at this time it's getting dark, which in a way is a bit of a blessing. We can use that. So the DC10 switched on all of its external lights, all the strobes, the landing lights, everything. It was lit up like the proverbial Christmas tree. Now the Cessna is pretty hard to spot, but he had all his lights on as well, as cockpit lights, etc. They also descended now from 33,000 feet. They descended down in order to have a better chance of spotting him. Captain Vettel, of course, used all the resources he possibly could. So as well as him and his crew looking out the window, he had all of his passengers look out the window as well. They had something like 80 or 90 passengers on board. It was a pretty light load, but still 80, 90 sets of eyes looking out the window is much better than 4 sets of eyes. So everyone was looking out the window. He'd instructed them to look out using, this is a technique you get taught at PPL flying for visual awareness, looking out for other aircraft rather than just staring out of the window. If you do that, your eyes have a natural tendency, if there's nothing to focus on, just to focus on a point at infinity. So what you do, you move your eyes round in just little sharp darty movements, then you go down and you scan across. So you just scan little bits of sky with a little pause in between them. It's a more effective method of scanning. You're more likely to pick up movement, for instance, by doing that rather than just staring at a spot. And the Cessna is going to be a particularly hard target to spot. But anyway, they got all the lights on and they're flying around where they think is his position, but they're just not seeing each other. So, of course, the Cessna pilot, who's been flying now for 19 hours or so, is getting very tired. He really doesn't know how much fuel he's got, so he's beginning to think about ditching in the ocean. But there's a twist. There's one final twist coming, and perhaps the most exciting twist of all. And for some reason, they didn't include this in the movie. I don't know why, because I think it's the best twist of all. It's the unexpected ending, but they didn't incorporate it into the movie. In fact, the movie went off on some other sort of tangent altogether. They, like I said earlier, in the movie they had this big storm move in, and it was all a bit dramatic. That's not really what happened in the actual incident. There was no storm, there was no heavily pregnant wife, and there was no bad guy. But so the Cessna's flying along in the dark now, thinking about ditching, when all of a sudden he sees lights, but not the lights of the DC-10 somewhere above him. He saw lights down in the ocean, and he says, I see lights, I see lights. And he goes down to check it out. So he comes down from 8,000 feet down towards the ocean floor, and he sees this big tall structure all lit up, and it's got some tugboats on it. And it turns out it's an oil rig being towed out somewhere into the ocean. An oil rig. Well, that's a bit of luck. So the DC-10 quickly gets onto Auckland air traffic, who in turn get onto the maritime authorities, and they try and work out what oil rig this could possibly be and if they could contact it. And it turns out it was an oil rig called the Penrod, which was being towed from, I think it was Sydney to Singapore. So a long old ocean crossing. So this is great. They know what this oil rig is. If they can contact it, they can work out exactly what position it is. So they do. It takes a few agonizing minutes for the information to be requested and passed back. But eventually they contact the oil rig, who passes their position, which is passed to Auckland Air Traffic Control, which is passed back to the DC-10. So it's gone through, who knows, 3 sets of ears. It's a bit like Chinese whispers. And eventually they plot, the DC-10, they plot the position, the reported position of this oil rig. And the exact position, I wrote it down here, that passed to them was at 31 degrees south, 179 degrees east, and some minutes. So when they plot that on their chart, they were absolutely dismayed to find that that was actually some 600 miles or more east of Norfolk. And they can't believe this. This is miles from where they thought it was, and certainly far beyond his remaining fuel endurance. If he's really at 600 miles from Norfolk, he's no hope. So they, with heavy hearts, pass this information to him. So he really now is starting to think about ditching. He goes down, but the ocean is actually pretty rough. It's got some very high waves, 15, 20 feet high waves, and in his little single-engine Cessna, it's going to be tricky, and he doesn't much fancy ditching into a dark ocean, even with the support of the tugs, who have spotted him. They're ready to try and fish him out of the water if need be. But how could they be so wrong? Well, whilst they're thinking about that, the DC-10 changes course and sets off towards this new position, 600 miles to the east of Norfolk Island, some 400 miles from where they are, nearly an hour's flying time. But it can't have made any sense to them, because everything they've done so far, all their techniques, the Aural search, the times of the sun setting, they all agreed with each other. They all heavily suggested that the Cessna was no more than 200 miles or so from Norfolk. So I'm a little surprised. Of course, they've all been at this now for many hours. They're all tired. But I wonder if... I'm kind of a little surprised they were so ready to accept this position of the oil rig without questioning it. I think given everything, you might think they would say, hang on, does that make sense? Is that right? So as they were flying down towards this new position some 400 miles away from them, they noticed something odd. That actually, instead of the radio transmissions between them and the Cessna getting stronger, because presumably they're now flying towards him, the signals are actually getting weaker. It seems like they're flying away from him. And actually, that's another thing. If they really were 400 miles away from his position, how is it they were talking on VHF radio? Because that's well outside the range that you would expect. So perhaps that was another clue that they might have picked up on. I'm not criticising for a second. These guys are superheroes in my book. But something was obviously not quite right. And the penny didn't drop until they were moving away and they were losing radio reception. So it was at this point that the crew, whether it was Vettel or someone else, said, hang on a second. This doesn't make any sense. So they went back. In fact, they got the frequency, the radio frequency for the oil rig itself, and they spoke directly to the oil rig crew and asked them directly what their position was, and they gave it as 31 south, 170 east, whereas before with the Chinese whispers message it had been given as 179. That's a whole 9 degrees difference. 9 times 60 is a lot of miles. So just a simple human error, unfortunately, there that meant that they'd been given the wrong position. But now they've got the right position, and actually it's great news because it places the Cessna pretty much where they thought, and in fact even slightly closer to safety at Norfolk Island. So the Cessna was about to ditch in the ocean, but in the nick of time, in good old Hollywood fashion, they were able to transmit the good news that in fact that was an error and he was much, much closer. And the rest of the story, well, you can read for yourself, but they quickly 180 degrees headed back in the right direction, and pretty soon actually they made visual contact. Okay, they flew right over the top of the Cessna. The DC-9 lit up like a Christmas tree, and he was able to lead the Cessna back to safety, back to Norfolk Island to make a successful landing. The Cessna was airborne for over 23 hours from taking off in Pago Pago to eventually landing in Norfolk. 23 hours, which is quite remarkable, for a single engine Cessna. Of course, he'd used good common sense, good airmanship. He'd leaned the mixture as far as he was able to. What does leaning the mixture mean? It's a carbureted engine, very simple engine. The fuel and the air mix in a particular ratio to give combustion. If that ratio is too rich, then it won't work. If it's too thin, it won't work. So there's an ideal ratio of fuel to air. And in most carbureted engines, aircraft, you've got a fuel nozzle. It's usually a red handle, and you can adjust it somehow to reduce the fuel-air mixture. So to lean the mixture back, it just basically means to pump less fuel into the carburetor to get a thinner mixture. So he'd obviously leaned, as soon as he realised something was wrong, had started to lean the mixture to conserve fuel as much as possible. But still, 23 hours. He must have been exhausted, but thrilled, I bet, to be back on dry land. For their efforts, for their fantastic skill, for their knowledge, for their initiative, and willingness to help, I guess, the crew of the DC-10, Captain Vetti in particular, and his navigator were awarded by GAPAN, that's the Guild of Air Pilots and Navigators. They were awarded the Malcolm Forsyth Trophy for outstanding airmanship, and they were also presented with awards by McDonnell Douglas as well, the manufacturer of the aircraft. So I think that concludes our story. I think that's a fantastic tale. I love the fact that they were able to use the sun, some basic knowledge, outstretched fists to overcome a problem which maybe to us mere mortals might have seemed an impossible challenge. Not sure if I could have come up with a similar feat like that, but I think it's something to be admired, certainly.